3 weeks ago, in a paper buried inside a physics journal almost no one outside the field has heard of, a team at CERN quietly published a number that may turn out to be the most important crack in our understanding of reality in 50 years. 4 sigma. A 1 in 16,000 chance it is just noise. The first surviving signal of new physics from the Large Hadron Collider in 5 long, silent years. Tonight we're going to find out what they saw, what it might mean, and why the people who built the most powerful machine in human history are too cautious to say it out loud yet. So go ahead, get comfortable, hit subscribe, and let's get into it. Part 1. The Whisper in the Data. 3 weeks ago, on the 20th of April 2026, in a quiet announcement buried in the pages of Physical Review letters, a team of physicists at CERN published a result that, depending on which way the next 2 years of data fall, will either be remembered as a statistical ghost or as the moment the standard model of particle physics started to break apart for the first time in 50 years. The paper is dense, the language is careful, but the number at its centre is impossible to ignore. 4 sigma. A 4 sigma deviation from what the most successful physical theory ever written predicts should have happened inside a particle accelerator 27 kilometers long, buried 100 meters beneath the border of France and Switzerland. I want you to sit with that for a second. 4 sigma. In particle physics, that translates to roughly a 1 in 16,000 chance that what they saw is just noise, not a coin flip, not a coincidence, not a glitch in the detector, because they spent 13 years checking and rechecking and rechecking. They have been hunting for cracks in the standard model for so long, with such precision, that when something this size finally appears, the entire field stops breathing. And here is the part that nobody is quite saying out loud yet, the part that the people who built the cathedral are too cautious to put in a press release. This is the first real, surviving multi-sigma anomaly to come out of the Large Hadron Collider in 5 years. The first one in 5 years that hasn't quietly evaporated under more data. The silence has been broken. Maybe. The experiment is called LHCb. It sits in one of the 4 main caverns along the LHC ring, and unlike its more famous cousins Atlas and CMS, which were designed to look for new heavy particles popping into existence at the energy frontier, LHCb does something subtler. It studies how particles called B-mesons fall apart. B-mesons are tiny, short-lived objects that contain a beauty quark, sometimes called a bottom quark, and they exist for less than a trillionth of a second before they disintegrate into other things. Most of those disintegrations are boring. The standard model predicts them perfectly. But occasionally, very occasionally, a B-meson does something rare. Specifically, the beauty quark inside it transforms directly into a strange quark, and in the process it spits out 2 muons, which are basically heavy electrons. This kind of decay happens about once for every million B-mesons. The rest of the time the beauty quark turns into a charm quark instead, which is the boring expected outcome. So LHCb has spent its entire existence sifting through staggering numbers of collisions, looking specifically for that rare, suppressed 1 in a million decay. The data set they used for this particular analysis was collected between 2011 and 2018. Approximately 650 billion B-meson decays. 650 billion. To find the rare ones. They studied a specific decay called B0 into K star into K plus pi minus mu plus mu minus, which is a mouthful, so let me put it in plain language. A B-meson breaks into a kaon, a pion, and 2 muons. The geometry of how those 4 particles fly out, the angles between them, the distribution of their energies, all of it is predicted by the standard model with extraordinary precision, because the decay is so rare and so suppressed that it can only happen through what physicists call virtual quantum processes. Particles that pop out of empty space, do their job, and pop back in before anyone can see them. Because the prediction is so tight, even a small deviation from it shows up clearly, and the deviation they found shows up in an angular observable called P5', which I promise is the last bit of jargon I'll throw at you for a while. P5' is essentially a number that captures the shape of how those particles fly apart. The standard model says it should be one thing. The data says it is something else, by 4 sigma. Here is why this should make the hair on the back of your neck stand up. The standard model is the most rigorously tested theory in the history of science. It predicted the W boson, the Z boson, the top quark, the Higgs boson, all before any of them were detected. It has passed every experimental challenge thrown at it for half a century. The standard model is so good that physicists have spent the past 50 years quietly hating it, because they know it can't be the whole story. And yet every time they probe it, it stares back at them and tells them, calmly, that it is, in fact, holding up just fine. And now, after a decade of nothing, after billions of dollars spent, after 30 years of design and construction and operation, after the discovery of the Higgs and the deafening silence that followed, this thing has appeared. But the people who built the cathedral are still being careful, and there's a good reason for that. Inside the LHCb result there is a complication, a standard model fudge factor with the wonderful name of charming penguins. Charming penguins are not a band. They are not a fringe theory. They are a higher order standard model process where charm quarks briefly contribute to the decay through diagrams that, with a bit of imagination, look like little penguins on the page. The problem with charming penguins is that they are notoriously difficult to calculate from first principles. They live in a regime where the math gets nasty, where the strong nuclear force becomes non-perturbative and the equations stop having clean solutions. So there is a real possibility, a non-trivial possibility, that the 4 sigma deviation isn't new physics at all. It might just be that the standard model prediction is slightly off, because the charming penguin contribution is bigger than current calculations suggest. The team has looked at this carefully. They have used the best available estimates, and those estimates say the penguins are not big enough to explain the discrepancy, but the calculations are tricky enough that nobody can be completely sure yet. So here is where we stand, 3 weeks after the announcement. LHCb has, for the first time in 5 years, produced an anomaly large enough that statistical noise alone is almost certainly not the answer. They have already collected 3 times more B-meson data than was used in this analysis. They are processing it now. The high luminosity LHC, which begins operations around 2030, will eventually multiply that dataset by another 15 times. There is no middle ground left. Within the next 2 to 5 years, the 4 sigma will either climb to 5 sigma, which would constitute a genuine discovery and the first crack in the standard model in half a century, or it will collapse back to nothing, joining the long graveyard of anomalies that have flickered into existence and faded out again over the past decade. There is no scenario in which it stays at 4 sigma forever, the cathedral whispered. We are about to find out whether it was speaking, or whether what we heard was just the building settling. And that question, that one specific question, is what this entire video is about. Because it is part of a much larger story, a 30-year story, about what we built that machine to find, what we expected to find inside it, and the strange and unsettling thing that has happened in the time since. The most powerful microscope ever pointed at reality has, by the act of seeing nothing where it was supposed to see everything, started telling us something we're not yet ready to hear. Part 2. Why that whisper terrifies physicists. To understand why a 4 sigma blip in a B-meson decay is keeping particle physicists up at night, you have to understand what the past decade inside that field has actually felt like. And I want you to think about this honestly, because the popular image of physics is still stuck somewhere around the Higgs announcement of 2012, when it looked like the field was on the verge of unlocking the secrets of the universe one by one. The reality since then has been much, much stranger. After the Higgs was found, physicists waited for the next thing. They were not waiting hopefully or speculatively. They were waiting with confidence, because the textbooks they had been writing for 2 decades told them, in numerical detail, what the next thing should be. Supersymmetric particles, dark matter candidates, maybe extra dimensions, maybe even tiny black holes. They had calculated the masses, the production rates, the expected signatures in the detectors. They had built ATLAS and CMS specifically to catch those signatures. The Higgs, in many ways, was the appetizer. The main course was supposed to come next. It did not come. Run 1 ended, and nothing. Run 2 ran from 2015 to 2018. Nothing. Run 3 started in 2022, with the highest collision energies ever achieved, and as of right now, with the dataset still growing, still nothing. Anomalies appeared. Theorists wrote hundreds of papers in a frenzy, and then the anomalies disappeared. The 750 giga-electron-volts diphoton excess of December 2015 lit up the entire field for 6 months, and then evaporated like fog when more data came in. The Bemis and Lepton universality anomalies, which were supposed to be the smoking gun of new physics throughout the late 2010s, slowly, painfully, faded away during the reanalyses of 2022 and 2023. The famous muon G-2 anomaly, the one that made every science magazine cover for years, has had a strange slow-motion death this past year that we'll get to later. But the short version is that the experimental side closed in June of 2025, and the theory side has been moving in the wrong direction for new physics ever since. So when I tell you that the 4 sigma LHCb result that just came out is the first real, surviving anomaly in 5 years, I want you to feel the weight of those 5 years. They were not idle. They were not empty. They were 5 years of data pouring in, of hopes lifting and falling, of grad students writing thesis chapters that had to be rewritten when the bumps in the data smoothed themselves out. This is why the LHCb result terrifies people, and I'm using the word terrify carefully here. Physicists are not afraid that they have found something. Physicists are afraid because they have wanted to find something for so long that even a maybe signal lands like a thunderclap in a quiet room, and the temptation to over-interpret is enormous. They have been disappointed so many times that the institutional muscle memory now is to be skeptical, careful, methodical, to check the calibrations, to verify the systematics, to wait for more data. Because if this one fades the way the others did, after the way it has been hyped in the press over the past 3 weeks, the credibility of the field takes another hit. And the field cannot afford another hit. But there is a second layer of why this whisper is so unsettling, and it has nothing to do with public relations. The LHCb result is not just any anomaly. It is sitting in exactly the place where, theoretically, you would expect new physics to first appear. Rare decays of B mesons are extremely sensitive to the existence of new heavy particles, because those new particles can secretly contribute to the decay through quantum loops, even if the new particles themselves are too heavy to be produced directly in the collisions. So a 4 sigma deviation in this specific channel is not just a statistical curiosity, it is potentially an indirect echo of something massive sitting just beyond the energy scales that the LHC can reach directly. A leptoquark, a Z-prime boson, some new force we have not yet named, leaving a fingerprint in the geometry of how a kaon and a pion and 2 muons fly apart in a Swiss cavern. That is, of course, the optimistic interpretation. The pessimistic interpretation, the one I mentioned earlier, is that the charming penguins are eating us. Higher-order standard model processes that we cannot calculate well enough are mimicking the appearance of new physics. This has happened before. There have been multiple times in the history of particle physics where a deviation that looked like a smoking gun turned out to be a theoretical mistake, a place where the existing math was being asked to do too much. And the honest truth is that with current techniques we cannot rule that explanation out at this moment. We can disfavour it. We can suggest that the deviation is a little too large to be absorbed by penguin effects at their plausible upper bound. But we cannot rule it out. So the 4 sigma result is genuinely ambiguous, and the people who understand it best are the most cautious about what it means, which is exactly the situation that makes for a good cliffhanger, and exactly the situation that should make you, the viewer, want to keep going. Because here is the part of the story that the headlines about the LHCb result are missing. This anomaly is not a standalone event. It is happening inside a much bigger pattern, a 30-year pattern that the field is still trying to make sense of. The whisper in the LHCb data is the latest data point in a 30-year story about a machine that was built to find specific things, that has not found those things, and that has, by the very act of not finding them, told us something very strange about the universe. So before we go any further, before we walk through what the LHCb result might mean, and what is happening a mile beneath South Dakota, and what physicists are quietly considering as their next move, we need to back up. We need to talk about the cathedral itself. The thing that was built to answer the question, and what it has actually told us in the 30 years it has been listening. Part 3. The Cathedral and the God that didn't show up. Let me take you to the place where all of this is happening, because I think people throw around the words Large Hadron Collider without really feeling the scale of what we are talking about. So picture this. Beneath the border between France and Switzerland, at depths ranging from 50 meters to 175 meters depending on the terrain above, there is a circular tunnel 26.7 kilometers in circumference. That is roughly 16.6 miles. If you laid that tunnel out as a straight line, it would stretch from downtown Manhattan past JFK Airport. The tunnel was originally dug in the 1980s for a different machine called the Large Electron-Positron Collider, which is why it was already there when CERN decided to build something bigger inside it. Inside that tunnel, there are 1,232 superconducting dipole magnets, each one weighing about 35 tons, all cooled to a temperature of 1.9 Kelvin. To put that in perspective, the average temperature of empty space, far from any star, sits around 2.7 Kelvin. The magnets in the LHC are colder than the vacuum between galaxies. They're cooled using superfluid helium, which is itself one of the strangest substances in the known universe, a liquid that flows without any friction and can climb up the walls of its container if you're not careful. The total mass of all that cold material is around 37,000 metric tons. It is, by some measures, the largest cryogenic system ever built. Inside the magnets, two beams of protons travel in opposite directions, packed into bunches of about 100 billion particles each, with up to 2,808 bunches per beam. The protons move at 99.9999991% of the speed of light. The beams cross at 4 collision points, where the bunches slam into each other 40 million times every second. At the highest energies the LHC has reached so far, in the current run 3, the center of mass collision energy is 13.6 tera electron volts. That number is meaningless without context, so here it is. 13.6 tera electron volts is the energy density that the universe last had a fraction of a second after the Big Bang. The LHC, in its collision points, is briefly, locally, recreating conditions that have not existed naturally in our universe in nearly 14 billion years. The total cost to build this thing was about 4.75 billion Swiss francs, which translates to roughly $5.5 billion in current terms. CERN, the organization that runs it, employs more than 17,500 people across 23 member states. The data the LHC produces is processed across a global computing grid that spans about 170 facilities in 42 countries. It is, by every reasonable measure, the largest, most expensive, most ambitious scientific instrument human beings have ever constructed. We did this. The species that mostly fights about borders and paychecks, in the same century, also did this. And here is where the title of this video starts to mean what it actually means. The thing the public knows the LHC for is the discovery of the Higgs boson on the 4th of July 2012. We will get to that in detail. But I want you to understand something first because it changes everything that follows. The Higgs was not really the reason we built the LHC. The Higgs was, in some sense, the bait. It was the predicted particle that physicists could point to in their funding proposals and say, look, we know this is there, and we know roughly where its mass should be, and if you give us 4.75 billion francs, we will find it. And they did. The Higgs was, by 2012, a near certainty. The theoretical bounds on its mass had become so tight by the early 2000s that finding it was a question of when, not if. Building the LHC just to find the Higgs would have been, in the cold accounting of large-scale physics, a slightly disappointing outcome. The real reason we built that machine, the actual reason that physicists spent 30 years lobbying governments, the reason countries from 23 different member states agreed to pour billions of dollars into a hole in the ground in the Swiss countryside, was the conviction that the LHC would find the next layer of reality. Not just the Higgs. After the Higgs, the supersymmetric partners, the dark matter particles, the hidden dimensions, the Kluser-Klein excitations, possibly the hidden sector with its own forces and matter content, possibly the production of microscopic black holes evaporating through Hawking radiation in the detectors. The textbooks written in the 1990s and the early 2000s named the particles that were going to show up. They had charts. They had predictions. They had specific mass ranges. The Higgs was supposed to be the easy part. The hard part was the rest of it, and the hard part was where the truly transformative discoveries were going to be. 30 years later, here is what we have actually got. We have the Higgs, and we have, almost everywhere else, a vast and accumulating silence. Here is a phrase I want you to hold in your head for the rest of this video, because we are going to come back to it more than once. The cathedral was built. The God did not show up. Right now, that phrase probably sounds like a punchline. By the end of this script, I hope it sounds like something heavier than that. Something more like an honest description of where the smartest people on Earth are in 2026, after 30 years of looking. And the question we're going to spend the next 2 hours circling is the question that has come back into focus in the last 3 weeks because of LHCb, which is, if the cathedral was built and the God did not show up, what was the silence telling us? Were we listening for the wrong God, or were we all along in the wrong building? Part 4. The textbook predictions of 1995. To feel the weight of what has and hasn't happened, you have to understand what physicists genuinely thought, with high confidence the LHC was going to find. And I want to do this with specifics, because if I just tell you that they expected new particles, and that no new particles were found, that doesn't really land. The textbook predictions of the 1990s were not vague hopes. They were detailed, calculated, mass-ranged, cross-section quantified expectations, and the people writing those textbooks were not cranks or dreamers. They were, almost without exception, the most respected theorists in the field. The single biggest expectation was supersymmetry. Supersymmetry, which everyone in the trade calls SUSY, is a theoretical extension of the Standard Model that was first proposed in the 1970s. The basic idea is elegant. Every known particle, every quark, every electron, every photon, every gluon has a heavier partner particle, a superpartner, that is identical to it in almost every way except for one specific quantum property called spin. Quarks have squark partners, electrons have selectron partners, the photon has a photino, the Higgs has a Higgsino. The whole catalogue of the Standard Model gets a mirror catalogue, and that mirror catalogue, once you wrote it out, did something beautiful for the physics. It solved the so-called hierarchy problem. The hierarchy problem is the fact that the Higgs mass should, according to quantum mechanics, get blown up to enormous values by quantum corrections from heavy particles. We know it doesn't, because we have measured the Higgs, and its mass is a very pedestrian 125 gigaelectron volts, but the math says it should be much heavier unless something cancels those corrections. Supersymmetry cancels them, naturally and beautifully, but only if the superpartners exist at energies near the TV scale, which is exactly the scale the LHC was designed to probe. The minimal supersymmetric Standard Model, the basic vanilla version of SUSY, predicted superpartner masses in the range of hundreds of gigaelectron volts up to about 1 teravolt, squarely in LHC territory. Theorists wrote endless papers about which superpartner would show up first, what it would decay into, what the signature in the detector would look like. By the early 2000s, supersymmetry was so widely accepted as the next layer of physics that it was taught alongside the standard model in graduate courses, not as speculation, as the natural next chapter of the same story. And here is where it gets interesting, because supersymmetry didn't just solve the hierarchy problem, it also gave you something else for free. The lightest superpartner, in most versions of the theory, was stable, electrically neutral, and weakly interacting. Which is to say, it was a perfect candidate to be dark matter. This single biggest unsolved problem in cosmology, the question of what makes up roughly 27% of the mass energy of the universe, would be solved automatically as a side effect of solving the hierarchy problem. Two unrelated mysteries collapsing into one solution. That is the kind of theoretical elegance that physicists die for. It was frankly too good to be true, and it should have shown up in the LHC data. Not maybe, not eventually. The simplest, most natural versions of SUSY predicted clear, unmistakable signatures in the detectors, and those signatures should have started appearing within the first year of LHC operations. Beyond supersymmetry, there were other predictions, equally serious. In 1998, 3 physicists named Arkani Hamed, Dimopoulos, and Diwali proposed something radical. They suggested that gravity is so much weaker than the other forces because it leaks into extra spatial dimensions that we can't see. The model came to be called the ADD model, after their initials. A year later, in 1999, Lisa Randall and Raymond Sundram proposed a related but different framework, the Randall-Sundram models, where the extra dimension is warped in a specific way. Both frameworks made a startling prediction. If extra dimensions exist at the right scale, then the energy at which gravity becomes strong, the so-called Planck scale, might not be at the absurdly high 10 to the 19th giga-electron-volts we'd always assumed. It might be down at the TeV scale, which would mean that the LHC, when it turned on, might briefly produce microscopic black holes in its collisions, black holes that would evaporate almost immediately through Hawking radiation, giving off detectable signatures in the detectors. Now this is where the public got nervous in 2008, when the LHC was first turning on, because there were these viral claims that the LHC was going to produce a black hole that would consume the Earth. We will deal with that whole conspiracy thread later. The short answer is that even if the LHC did produce micro-black holes, they would evaporate in less than a billionth of a second, and the same energies are achieved every day in the upper atmosphere when cosmic rays slam into nitrogen molecules, and the Earth is still here. But the point I want to make right now is that the production of micro-black holes was a serious scientific prediction in the late 1990s and early 2000s. It was not science fiction. It was a published peer-reviewed possibility, with calculated cross-sections and predicted signatures, and the LHC was, in part, built to test it. There was also the prediction of WIMPs, weakly interacting massive particles, which is the canonical dark matter candidate. The expected mass range was anywhere from 10 giga-electron-volts to a few tera-electron-volts, and the expected interaction strength was at the weak scale. There was even a beautiful coincidence called the WIMP miracle, where if you assumed a particle with the right mass and the right interaction strength, the calculated abundance of those particles left over from the Big Bang exactly matched the observed dark matter density today. The numbers just worked. Which suggested very strongly that the dark matter was exactly the kind of particle the LHC could produce. There were also predictions for hidden sectors, dark photons, Kaluza-Klein excitations, leptoquarks, axion-like particles. The textbooks of the late 1990s were a parade of expected discoveries, each one with detailed predictions about how it should manifest in the data of a sufficiently powerful collider. The LHC was built, and the LHC ran, and the LHC has now been running for over a decade. The result, as we're about to walk through, is that of all those predictions, every single one except the Higgs has either been ruled out entirely, pushed to scales the LHC can't reach, or quietly removed from the textbooks. The cathedral was built, the god did not show up. But before we get to that silence, We have to talk about the one time the cathedral worked exactly as designed. The one moment in the past 30 years when prediction and experiment met and history was made. Part 5, July 4th, 2012. I want you to come with me to a specific room on a specific morning, and I want to take it slow, because what happened in that room is the high-water mark of 21st century physics, and everything that follows in the story is in some sense measured against the silence that came after. The room is the main auditorium at CERN in Geneva. The date is the 4th of July 2012. The time is around 9 in the morning Geneva time. The auditorium is full. There are physicists who have flown in from around the world. There are reporters. There are graduate students who slept overnight in the hallways outside to make sure they got a seat. And in the audience, in one of the front rows, there is an 83-year-old British physicist named Peter Higgs. Peter Higgs published the paper that predicted the existence of the particle that now bears his name in 1964, 48 years before this morning. He proposed a mechanism by which the fundamental particles of the universe acquire mass, through their interaction with an invisible field that fills all of space. The field came to be called the Higgs field, and the particle predicted by exciting that field came to be called the Higgs boson. For nearly 5 decades, Peter Higgs lived with the strange, surreal experience of being the man whose name was attached to a particle that had not yet been seen, and which might never be seen, and which was, in some quiet way, the missing keystone of the entire edifice of modern physics. On this morning, the spokesperson for the Atlas experiment, an Italian physicist named Fabiola Gianotti, walks to the podium. The room is silent. She begins to present data. Slides go up. There is, somewhat famously, a Comic Sans font on those slides, which became a small joke afterwards, because the most important physics announcement of the century was delivered in a font usually reserved for elementary school flyers. Gianotti walks through the analysis methodically, the collisions, the decay channels, the expected backgrounds, and then she shows the plot, a bump in the data, at 125 giga-electronvolts. The statistical significance, she says, is 5 sigma. That is the threshold for a discovery. That is the threshold above which the chance of statistical fluke is so small that the physics community accepts the result as real. In the audience, Peter Higgs takes off his glasses. He wipes his eyes with the back of his hand. He is photographed doing this, and the photograph travels around the world within hours. 48 years of his life, ending in this room, with a graph showing a bump where he had predicted there would be a bump. He says afterwards, quoted in the press, that it is incredible to him that this thing happened in his lifetime. The CMS spokesperson, Joe Incandela, gets up next and presents the same result from the other detector independently. 2 experiments, 2 teams who had been kept separate from each other's data to avoid contamination, both seeing the same bump in the same place at the same significance. A year later, in 2013, Peter Higgs and François Englert, a Belgian physicist who had independently proposed a similar mechanism in 1964, share the Nobel Prize in Physics. Now, I want to be clear about what this moment was and what it wasn't, because the popular memory of it has gotten a bit muddled. The Higgs discovery was, scientifically, exactly what was expected. It was a triumph of prediction and experiment lining up the way they are supposed to. The theorists had been telling the experimentalists for years where to look and what to look for. They had narrowed the possible mass range. They had calculated the production rates. They had predicted the decay channels. The Higgs at 125 giga-electronvolts was, by 2012, almost a foregone conclusion. What was not foregone, what was not certain, was that nature would actually be kind enough to put the particle right where the simplest version of the theory said it should be. Sometimes nature is not kind. Sometimes the math works on paper, but the universe decides to do something else. On the 4th of July 2012, nature was kind. The simplest version of the theory turned out to be correct. And here is the part that very few people remember about that day, the part that I think is critical for understanding what came next. While Peter Higgs was wiping his eyes in the front row of that auditorium, somewhere in the back of his mind and in the minds of every other theorist in the room, a clock had started ticking. Because the discovery of the Higgs, in the specific way it was discovered, with its specific properties, with its specific mass, raised an immediate, urgent, deeply uncomfortable question. The question was this: if the Higgs is just sitting there at 125 giga-electron-volts, with no friends, no superpartners, no exotic decay modes, no hidden sector mediators, then the hierarchy problem is not solved by anything we know about. The Higgs mass is exactly where it shouldn't be, naturally, unless something else is there to protect it. And the something else was supposed to be the next discovery. The next discovery did not come. The Higgs was found in 2012. We are now in 2026, 14 years later. In those 14 years, the LHC has run nearly continuously, has accumulated more than 250 inverse femtobarns of data, which translates to roughly 25,000 trillion proton-proton collisions across both general-purpose detectors. And in all of that data, in all of those collisions, with all of that energy, with all of that statistical power, the only major new particle that has been discovered is the one we already had reasons to expect. Everything else, every single one of the predicted next-layer particles from the textbooks of the 1990s, has been pushed into the territory of either total exclusion or extreme uncomfortable fine-tuning. Peter Higgs lived to see the discovery of his particle. He passed away in 2024 at the age of 94. He did not live to see the rest of the predicted discoveries arrive. Neither, it is becoming increasingly clear, will most of the people working on the LHC today. So that brings us to the part of the story that almost nobody outside the field talks about, which is what has actually happened in those 14 years of silence. Because the silence was not an absence of activity. The silence was the sound of one of the largest experimental programs in human history, methodically ruling out the answer they had been told, with confidence, was waiting for them. Part 6. The exclusion plots get tighter every year. Here is something that does not make the news, because it is not the kind of thing that makes for a good headline, but it is, I think, one of the most important scientific stories of our time. Every single conference where particle physicists gather, every Morion meeting in March, every ICH-EP meeting in the summer, every winter retreat, the same thing happens. The collaborations at the LHC, mostly Atlas and CMS, present their latest analyses. They show their latest plots. And on those plots, you can see the boundaries of what has been ruled out. Those boundaries are called exclusion limits, and the regions inside the boundaries are the places where new particles cannot exist, consistent with the data. Every conference, those boundaries get a little wider. Every conference, the regions where new particles could still be hiding get a little smaller. The exclusion plots, in other words, are eating the available territory. And the territory they are eating was, 20 years ago, the territory where everyone was sure the discoveries would be. So let me give you specifics, because this is the part where the silence becomes quantitative. As of right now, in 2026, Atlas and CMS have excluded gluinos, which are the supersymmetric partners of gluons, with masses below approximately 2.3 TeV in the simplest models. They have excluded squarks, the partners of quarks, below about 1.85 TeV. They have excluded stops, the partners of top quarks, below about 1.25 TeV. The natural SUSY parameter space, the region where supersymmetry would actually do its job and solve the hierarchy problem cleanly, has been comprehensively, exhaustively ruled out. In March of 2026, just a few weeks ago, the Atlas collaboration presented 45 separate analyses at the Morion conference. These were updated analyses combining the full Run2 dataset from 2015 through 2018 with the still growing Run3 dataset that started in 2022. Some of these analyses use machine learning techniques, neural networks specifically trained to look for SUSY signatures in places where standard analyses couldn't quite reach. There was a particularly striking one looking for what are called compressed Higgsinos, which are very specific supersymmetric particles that decay to almost invisible signatures, leaving behind disappearing tracks in the detector. The neural networks were able to find regions of phase space that had been inaccessible before, and in those regions, Atlas for the first time set chargino and neutralino mass and lifetime limits that surpassed the long-standing bounds set by the LHC's predecessor, the Large Hadron Collider, way back in the 1990s. Limits that had stood for 30 years were finally exceeded, and in the process of exceeding them, no new particles were found. I want to be careful here, because I don't want to make supersymmetry sound dead. It isn't. Theoretical physicists are still working on more exotic, more contrived versions of SUSY, where the superpartners are heavier than the LHC can reach, or where they decay in ways that the LHC searches haven't been optimized for. But those versions are by their nature less natural. They require fine-tuning. They require putting the superpartners at masses where they can no longer cleanly solve the hierarchy problem. The whole reason supersymmetry was the dominant framework for 40 years was that it solved a specific problem in a natural way at TV-scale energies. If you push the superpartners up to 10 TeV or 100 TeV, the theory becomes ugly, the cancellations stop being natural, and the original motivation for the framework starts to dissolve. So when physicists talk about the LHC having killed SUSY, what they actually mean is that the LHC has killed natural SUSY, the version that was supposed to elegantly solve the hierarchy problem, the version that came with a free dark matter candidate as a bonus. That version is gone, but that is just supersymmetry. The same process has happened, almost identically, with every other category of predicted new physics. Extra dimensions of the ADD type, the ones that would lower the Planck scale to TeV energies, have been excluded all the way up to fundamental Planck scales of about 10 TeV, which means that if extra dimensions exist, they exist at energies the LHC cannot reach. Micro-black holes, the predicted signature of low-scale quantum gravity, have not been observed in any of the 250 inverse femtobarns of data collected so far, not a single event. Which empirically confirms what cosmic ray physics had already established, that the LHC was not going to destroy the world, because the universe has been doing LHC equivalent collisions in Earth's upper atmosphere for billions of years and we are still here. WIMPs, the canonical dark matter candidates, have not been produced in any of the LHC searches at any of the energies tested. Hidden sectors, dark photons, all of it. No clear resonances detected in mass ranges accessible to the LHC. Now, while the LHC has been doing its work above ground, there has been a parallel hunt going on. A hunt that does not involve smashing particles together, but rather the opposite. A hunt that involves sitting very still, deep underground, waiting. And that hunt has produced a result just a few months ago that is in some ways even more disturbing than the LHC silence. Because if the LHC silence tells us that the dark matter is not at the energies we can probe in collisions, the underground silence tells us something even harder to absorb. It tells us that we may be approaching a physical fundamental wall, beyond which finding the dark matter through the methods we have been using becomes impossible. Not difficult, not expensive, impossible. And that wall, as it turns out, was placed there by the universe itself. So, what is the wall? What did the world's most sensitive dark matter detector see on the 8th of December 2025 that has changed the way physicists are talking about the entire field? Let's go down, a mile down, into a former gold mine in South Dakota where 7 tons of liquid xenon have been waiting, in the dark for years, for a single touch from a single dark matter particle, and where, instead, they just heard something else. Part 7. The Underground Cathedrals. Imagine a place where, in order to do your science, you first need to ride an elevator down a mile into the Earth. That is the working environment of the people running the Lux Zeppelin experiment, abbreviated as LZ, in the Sanford Underground Research Facility in South Dakota. The site used to be the Homestake Gold Mine, the deepest gold mine in North America, which closed in 2002 after over a century of operation. When the mining ended, the laboratory began. And what they built there, in a cavern thousands of feet beneath the surface, is one of the strangest and most beautiful pieces of scientific equipment on Earth. The detector is, at its core, a tank, a very specific, very engineered tank. Inside it sits 10 metric tons of liquid xenon, ultra-pure, ultra-cold, kept at -100 degrees Celsius. The xenon is surrounded on every side by photodetectors, hundreds of them, all facing inward, all watching. The entire tank is shielded by an outer water tank to absorb any stray radioactivity from the rocks around it. The whole apparatus is sitting under a mile of solid rock, which itself is a shield, designed to block out the constant rain of cosmic rays that bathe the surface of the Earth at all times. The whole point of going underground is to get away from the noise of cosmic rays, the noise of background radioactivity, the noise of the world, so that if a single dark matter particle, in its silent passage through the Earth, happens to bump into a single xenon atom, the resulting flash of light and electrons can be seen, recorded, and understood. And the same kind of experiment is happening in 2 other places on Earth, simultaneously. There is Xenon NT in the Gran Sasso laboratory, deep beneath an Italian mountain, with 5.9 tons of liquid xenon. There is Pandex 4T in the China Jinping Underground Laboratory, which is the deepest underground physics laboratory in the world, sitting beneath 2,400 meters of solid rock. 3 competing collaborations, all using essentially the same approach, all hunting for the same thing, all in the deepest, quietest, darkest places they can find on the planet. Now, I want to give you a sense of the sensitivity these things have reached, because the numbers are staggering, and they're getting more staggering every year. The XENONNT collaboration published their latest result in late November of 2025. They had collected 3.1 ton years of exposure, combining their first and second science campaigns. They saw no significant excess above the expected background. Nothing. And in the process of seeing nothing, they set the most stringent limits ever placed on dark matter cross-sections in their range. Specifically for a hypothetical dark matter particle weighing about 30 gigaelectronvolts per c², they ruled out interaction cross-sections above 1.7 times 10 to the -47 centimeters squared. That number is meaningless to anyone who does not work in particle physics, so let me translate it. The cross-section is a measure of how often a dark matter particle would interact with ordinary matter. The smaller the cross-section, the rarer the interaction. The Xenon-NT limit is roughly 6 orders of magnitude below where the WIMP miracle, the original prediction, said the dark matter should be detectable. We're now hunting for an interaction 1 million times rarer than the simplest theory predicted should already have been seen. So that is the picture. Going into December of 2025, 3 giant underground detectors, all of them running, all of them seeing nothing, all of them pushing the exclusion limits deeper and deeper, all of them eating the parameter space where the dark matter was supposed to live. The cathedral above ground at CERN was built, and the god did not show up. The cathedrals below ground, in South Dakota and Italy and China, were also built, also waiting, and the same god, in those silent halls, has so far not shown up either. And then, on the 8th of December 2025, the Lux Zeppelin collaboration walked into a scientific seminar at the Sanford Underground Research Facility and announced something that, depending on how you frame it, is either the greatest disappointment of the 21st century or the most subtly profound discovery in dark matter physics in a generation. Possibly both. Because what LZ saw, after 417 days of LEV data taking between March of 2023 and April of 2025, after assembling the largest dataset ever collected by any dark matter detector in history, was, on the dark matter front, exactly nothing. No WIMPs. Not in the standard mass range. Not for the first time in the low mass range between 3 and 9 gigaelectronvolts per c², which they had now extended their search into. World-leading limits, especially above 5 giga-electronvolts, but no signal, no discovery. What they saw instead, in the absence of any dark matter signal, was something else entirely. Something that, in a strange way, is even more troubling than the silence itself. Part 8. The wall the sun put there. I want you to picture yourself for a moment standing inside the LZ experimental hall, a mile beneath the surface of South Dakota. The lights are dim. There is a faint hum from the cooling systems. The xenon tank glows very softly at the temperature of liquid air. The photodetectors face inward, in concentric rings, each one no bigger than your fist, watching. The shielding rocks around you are billions of years old, formed when the Earth was still hot. The experiment has been running in this hall for years. The team has been waiting for a particular kind of event, a single, faint, double flash of light as a dark matter particle nudges a single xenon nucleus, gets the nucleus moving, and produces both an immediate flash of scintillation and a delayed flash from electrons drifting to the top of the tank. They have, in 417 days of data, waited for that signal, and the signal has not come. But while they were waiting, something else happened. The detector, in becoming sensitive enough to potentially see dark matter, also became sensitive enough to see something that physicists have known was coming for decades, and have, frankly, been dreading. They started seeing neutrinos. Not just any neutrinos. Boron-8 solar neutrinos. Neutrinos produced by fusion reactions in the core of our own sun. To understand why this is profound, and why physicists use the word fog or the word flaw, when they talk about it, you need to understand a specific physics process. It is called coherent elastic neutrino nuclear scattering, or CEVNES for short. CEVNS is what happens when a low-energy neutrino interacts with an atomic nucleus as a whole, instead of just hitting one of the protons or neutrons inside it. The neutrino bounces off the entire nucleus at once, like a pebble bouncing off a beach ball, transferring a tiny amount of energy that just barely shows up as a recoil. CEVNS was theoretically predicted in 1974. It was first observed experimentally in 2017, and the crucial catch for our story, is that the recoil signature from CEVNS looks almost exactly like the signature you would expect from a low-mass dark matter particle bumping into a xenon nucleus. This is what physicists have called, for years, the neutrino flaw or the neutrino fog. As your dark matter detector becomes more sensitive, eventually, inevitably, you reach a point where the background signal from solar neutrinos starts to mimic the signal you are trying to detect from dark matter, and once you reach that point, the noise from the neutrinos, which you cannot turn off because they are coming continuously from the sun, starts to compete with whatever dark matter signal might be present. You cannot shield against the neutrinos. They pass through a mile of rock as if it isn't there. The same sun that gives us light in the morning is, at every moment, soaking the entire Earth in a flux of neutrinos that no detector can shield against. And those neutrinos, in the rare events where they actually do interact, produce signals that look like dark matter. For decades, physicists have known this wall was coming. It is called a flaw for a reason. Once you are below it, you cannot easily go further. It is not a problem of building a bigger detector. It is not a problem of more money or more time. It is a fundamental sensitivity limit imposed by the fact that the sun exists and is doing its job. And on the 8th of December, 2025, Lux Zeppelin, the most sensitive dark matter detector ever built, became the first dark matter detector in history to cross into that regime at evidence-level statistical significance. They detected boron-8 solar neutrinos through the CEVNS process at 4.5 sigma. Earlier hints from Panda X4T at 2.64 sigma and from Xenon NT at 2.73 sigma had been suggestive but inconclusive. LZ pushed the significance over the 3 sigma threshold that physicists call evidence and approached the 5 sigma threshold for discovery. I want to slow down here because the implications of this are not getting talked about enough, and they should be. What just happened is that the world's most sensitive dark matter detector, while looking for dark matter, instead detected the neutrinos pouring out of the core of our own sun, through a process so rare it was only first observed 8 years ago, through a coupling that is so weak it took the largest dark matter detector in history to see it. And in seeing it, that detector confirmed, with strong statistical significance, that the next generation of dark matter searches, the experiments that come after LZ and XENO, and Panda X, will not be limited by background radioactivity, or by cosmic rays, or by detector imperfections. They will be limited by the sun, by the universe itself, by the unavoidable rain of neutrinos that the sun pours out at every second. So step back with me here, because I think the size of what has happened in the last 6 months has not really sunk in. We built the most powerful particle accelerator in human history, 27 kilometers across, beneath 2 countries, and after 30 years it has told us that the dark matter is not at the energies we can produce in collisions. We built the most sensitive direct detection dark matter experiments ever conceived, a mile underground, and after 2 decades they have told us that the dark matter is not at the cross-sections that the simplest theories predicted, and that we are now approaching a fundamental wall imposed by our own star. 2 completely independent approaches in 2 completely different regimes, both saying the same thing. The dark matter is not where we thought it would be, and we may be running out of room to look for it the way we have been looking. This is the part where the title of the video starts to mean what it means. Because if 95% of the universe is made of something that the largest machine we have ever built cannot produce, and the most sensitive detector we have ever built cannot see, and the next generation of detectors will be limited not by technology, but by the literal physics of our star, then what exactly is the silence telling us? And why, after a decade of that silence, is LHCb suddenly seeing a 4 sigma deviation in B meson decays that nobody can quite explain? Part 9, but we know it is there. Here is the dissonance at the centre of this entire story, the thing I want you to feel in your chest, because it is the reason this video is called what it is called. The dark matter is real. Let me say that again, more carefully. The cosmological evidence that something we cannot see, something that does not interact with light, something that outweighs all the visible matter in the universe by a factor of more than 5, is overwhelming. It is not a hypothesis. It is not a guess. It is, by every measure scientists have been able to apply, a settled empirical fact about the structure of the universe. The dark matter is there. We know it is there. The thing we do not know is what it is. The history of how we know this is, in itself, one of the great detective stories of 20th century astronomy, and I want to take a moment to lay it out, because I think when people first encounter the dark matter problem, they tend to imagine it as a kind of speculative extrapolation. It is not. It is the most thoroughly cross-checked claim in cosmology. The story really begins with an American astronomer named Vera Rubin, who in the 1960s and 70s started carefully measuring the rotation speeds of stars in spiral galaxies, starting with our nearest large neighbour, the Andromeda Galaxy. What Rubin found, working with her colleague Kent Ford, was something that did not make any sense under the existing physics. The stars at the outer edges of spiral galaxies were moving way too fast. So fast that, if the only mass in the galaxy were the visible mass we could see in the form of stars and gas, those outer stars should have been flung outward into space billions of years ago. Galaxies, as we observe them, should not exist. They should have come apart. Rubin's observations, repeated and verified across hundreds of galaxies in the years that followed, required something else, something invisible, something that was providing the gravitational pull to hold those galaxies together. The discrepancy, depending on the galaxy, required between 5 and 10 times more mass than the visible matter, and that mass, whatever it was, did not emit light, did not absorb light, did not interact with light at all. Rubin spent the rest of her career documenting this, and she was a very careful, very rigorous scientist, and the data she produced has stood for half a century. She passed away in 2016, having, in the eyes of many in the field, made the most important astronomical discovery of the 20th century and never received a Nobel Prize for it. Which is its own scandal, but a story for another video. The story did not end with rotation curves. It got, if anything, more solid as the evidence accumulated. In 2006, a team of astronomers studying a system called the Bullet Cluster published one of the most striking images in the history of astrophysics. The Bullet Cluster is two galaxy clusters, located about 3.7 billion light-years from Earth, that are in the process of colliding. Or rather, they collided about 150 million years ago, and we are seeing the aftermath now because of the time it has taken the light to reach us. When the two clusters slammed into each other, the hot gas in each cluster, which makes up most of the visible mass, got slowed down by collisional drag, just like two clouds running into each other. But the dark matter in each cluster, if it did not interact with anything, would have just kept going. It would have passed through, unimpeded, like two ghosts walking through each other. And here is the thing. When astronomers looked at the Bullet Cluster using X-ray telescopes, they could see exactly where the hot gas was. The gas, the visible mass, was slowed and concentrated near the centre of the collision. But when they used gravitational lensing, the technique of mapping where mass actually is, by looking at how it bends light from background galaxies, they found something else. They found that the bulk of the mass in the system was not where the gas was. The mass had passed through, separated from the gas, sitting in two clumps on either side of the collision. The mass and the matter were in two different places in the same image. You can pull the picture up online, you can see it for yourself. The gas glowing pink in X-ray, the mass shown as blue contours offset to either side. It is, I think, one of the most powerful pieces of evidence in all of cosmology, because it is a photograph, not a graph, not an inference. A picture, showing that there is a kind of matter in the universe that we cannot see, separated in physical space from the matter that we can. And then there is the cosmic microwave background, the leftover light from the universe when it was about 380,000 years old. We have measured the temperature variations in that ancient light to incredible precision, first with COBE, then with WMAP, then with the Planck satellite, which gave us our most precise measurements yet. The pattern of those variations encodes the entire matter-energy budget of the universe, because the size and the spacing of the temperature ripples depend on what was pushing and pulling on the early plasma. The third acoustic peak in the CMB power spectrum in particular is exquisitely sensitive to the amount of dark matter present in the early universe. And when you fit the CMB data to the standard cosmological model, you get a very specific number. You get that ordinary baryonic matter, the atoms that make up everything we can see, accounts for about 4.9% of the total mass energy of the universe. Dark matter accounts for about 26.8%. Dark energy, an entirely separate mystery that we're not even going to try to solve in this video, accounts for the remaining 68.3%. 5%. That is what we are made of. Atoms, stars, planets, galaxies, every piece of matter that has ever interacted with light in any way that we can detect. 5% of the total. The rest, the other 95%, is two different kinds of darkness. Dark matter, holding the galaxies together. Dark energy, accelerating the expansion of space itself. And we have, after 30 years of trying, no specific particle identified for either one. The cosmological evidence is unambiguous. The laboratory evidence is, on the question of identification, zero. So I want you to hold both of those facts in your head at the same time, because if you can hold them both, you are now feeling exactly the dissonance that the entire field of fundamental physics has been living with. 95% of the universe is missing. The largest machine we have ever built cannot find it. The most sensitive detectors we have ever built cannot find it, and we know, with overwhelming certainty, that it is there. It is passing through your body right now at hundreds of kilometers per second, at a density of about 0.4 giga-electron volts per cubic centimeter, near the surface of the Earth. Trillions of dark matter particles of whatever they are streaming through your living room as you watch this video. They have been doing it for the entire span of your life. They will continue to do it for the entire span of your life. And we, the species that built the LHC, that decoded the cosmic microwave background, that landed instruments on Mars, do not know what they are, have not seen one, cannot currently see one. Which forces us to ask the obvious question, the question that has been keeping the field up at night for the past 5 years, and that has become impossible to avoid in the past few months. What if we have been looking for the wrong thing all along? Part 10. The post-WIMP menu. I want you to picture a chalkboard in some theory office somewhere in 1995. On that chalkboard, in tidy handwriting, is a single word. WIMP. Weakly interacting massive particle. The candidate. The answer to the dark matter problem that almost everybody in the field believed was about to be confirmed. The chalkboard has one item on it. A single, beautifully simple proposal that solved everything. Now picture the same chalkboard in 2026. The word WIMP is still there, in the corner, with a small question mark next to it. Around it, filling the entire surface, are dozens of other proposals. Axions, dark photons, sterile neutrinos, primordial black holes, fuzzy dark matter, self-interacting dark matter, mirror matter, asymmetric dark matter, millicharged dark matter, freeze-in scenarios, dark matter with multiple components, dark matter that is not a particle at all, but a modification of gravity. The chalkboard is, in 2026, much more crowded than it was 30 years ago. And that is, in a strange way, a measure of how badly the original prediction failed. Because every time the original prediction got ruled out, theorists did not give up. They proposed something else. The dark matter candidate list is longer now than it was when the search started. Let me give you a sense of where some of the most active branches of that hunt are, because I think it tells you something about the state of the field. The most well-developed alternative to WIMPs is the axion, a hypothetical particle originally proposed in the 1970s to solve a completely different problem in physics, called the strong CP problem in quantum chromodynamics. The math worked out that if axions exist, they would also be a fantastic dark matter candidate, but at completely different masses than WIMPs. Axions would be ultralight, somewhere in the range of a millionth of an electron volt, which is about 100 million billion times lighter than a WIMP. To detect them, you cannot use a xenon tank. You need something completely different. The leading axion search experiment, called ADMX at the University of Washington, uses microwave cavities in strong magnetic fields to try to convert axions into detectable photons. It is a beautiful, clever, completely different kind of experiment from the underground xenon detectors, and it has been making real progress. In March of 2025, ADMX published a result excluding a specific theoretically motivated class of axions, the so-called DFS-Z axions, in the mass range from 3.27 to 3.34 microelectron volts. 8 months later, in November of 2025, they published a follow-up, extending the search into a different frequency range from 1.10 to 1.31 GHz, ruling out a broader class of axions called KSVZ axions. The axion search is real, it is making progress, and it has not so far found anything either, but the search is migrating methodically through the parameter space. There are sterile neutrinos, which would be right-handed neutrinos that interact only via gravity. They are being hunted at experiments like Microboon at Fermilab, with no detection yet. There are primordial black holes, which would have formed in the very early universe, possibly during inflation, and could account for some or all of the dark matter if their mass distribution falls in narrow allowed windows. The detection of unexpectedly massive black hole mergers by the LIGO and Virgo gravitational wave observatories has revived this idea in a serious way over the past few years. There is fuzzy dark matter, the idea that the dark matter is made of ultralight bosons, around 10 to the minus 22 electron volts in mass, with quantum mechanical wavelengths comparable to the cores of dwarf galaxies. There is self-interacting dark matter that can scatter off itself but not off ordinary matter, which would explain some small-scale structural problems with cold, dark matter simulations. There are dark photons, hidden sector particles that would be the bosons of an entirely separate force operating among dark matter particles. And then there is the most radical option, which is to question whether dark matter is a particle at all. The MOND framework, which stands for Modified Newtonian Dynamics, was first proposed by an Israeli physicist named Mordechai Milgram in 1983. MOND argues that maybe Newton's laws of motion need to be modified at very low accelerations, the kinds of accelerations you find at the outer edges of galaxies. If you tweak the dynamics in just the right way, you can reproduce galactic rotation curves without needing any dark matter at all. MOND has, surprisingly, fit galactic rotation curves better than dark matter does in some specific contexts. It has for decades struggled with the bullet cluster and with the cosmic microwave background, but it has not gone away, and theorists continue to refine it. There is also Eric Verlinder's emergent gravity proposal from 2016, which argues that gravity itself is an emergent phenomenon arising from entropic considerations, and that the dark matter effect might fall out of that framework as a side effect, rather than requiring any new particles. These are speculative. They are not the mainstream, but they are not crank theories either. They are the kind of thing serious theorists look at when the conventional answers keep failing to materialize. So here is the part that is genuinely strange. 30 years ago, the dark matter problem looked like it had one obvious answer: the WIMP. The prediction was tight, the experiments were clear, the discovery looked imminent. Today, after 30 years of searches, the answer space has, paradoxically, expanded. Because every confident prediction has been ruled out, and every new framework spawns its own set of particles to look for. The hunt has not narrowed. It has dispersed, and the field is, increasingly, in a posture of not knowing where to point its instruments next. Which brings us back to the LHCb whisper from a few weeks ago. Because in a field that has been listening to silence for so long, even a 4 sigma maybe signal does not just produce excitement, it produces a kind of theological event, the same way medieval villagers would have responded to a sudden flash in the sky. Modern theorists are looking at this anomaly and asking, with surprising openness, whether this might finally be the thing, whether the universe has decided after a decade of holding its breath to start talking again, and whether this time we're equipped to hear what it is saying. But before we get to whether the universe is talking, we have to talk about all the times in the past decade when the universe seemed to be talking and turned out, on closer inspection, not to be saying anything at all. Because the LHCb result is not the first whisper. It is just the first one in 5 years that has not yet collapsed. And to understand why physicists are being so cautious about this one, you have to understand the graveyard of anomalies that came before it. The places where, briefly, it looked like the silence had broken, and then the silence came rushing back. Part 11. The Vanishing Anomalies and the Survivors. Let me walk you through the graveyard. Not because it is depressing, although it is a little depressing, but because every tombstone in this graveyard is a story about how science actually works when it bumps up against the edges of what is known, and because the way each of these anomalies appeared and then disappeared shapes how the field is responding to the LHCb result right now. The most famous one, the one that probably caused the most heartburn in the entire past decade, was the 750 giga-electron-volt diphoton excess. In December of 2015, both Atlas and CMS, independently, reported a small bump in their data at a mass of about 750 giga-electron-volts in events where the collisions produced 2 high-energy photons. The bump was around 3 sigma in Atlas, and a bit lower in CMS, which sounds modest, but it appeared in both detectors in roughly the same place at the same time. The combined significance was tantalizing, and the physics community, after years of waiting for any sign of new physics, lost its mind. Within 6 months of the announcement, more than 500 theory papers had been written attempting to explain the bump. Each paper proposed a different model: new Higgs-like particles, hidden sector mediators, composite states, extra-dimensional Kaluza-Klein excitations. The conferences in the spring of 2016 were a kind of frenzy, with theorists arguing about which of the 500 explanations was most likely. I want to give you a glimpse of what that period felt like, because I think it tells you something important about what physics is actually like when it thinks it has caught a glimpse of new physics. Picture a theory seminar in the spring of 2016, somewhere like Princeton. The room is full. Speaker after speaker is presenting models that could explain the diphoton bump. Slides are dense with equations. The energy in the room is electric. A graduate student in the back is taking notes furiously, calculating in real time whether her thesis topic is still viable or whether she needs to pivot to one of the new frameworks being proposed at the front of the room. A senior theorist in the front row is asking pointed questions about whether the model being presented is consistent with electroweak precision data. The atmosphere is one of intense, slightly anxious excitement. Everyone in the room knows that this could be the breakthrough. Everyone in the room also knows that it might evaporate. But for these specific months, it does not feel like it will evaporate. It evaporated. By the summer of 2016, with new data from the next LHC run, the bump was gone. The signal that had looked so promising in 2015 had been, it turned out, a statistical fluctuation. 3 sigma fluctuations in a field where you are looking at thousands of possible signal regions are not actually that uncommon. That is what physicists call the look elsewhere effect. When you scan many possible places for a signal, the chance of seeing a 3 sigma fluctuation somewhere just by random chance is much higher than you might think. The 500 theory papers from the spring of 2016 quietly became unread papers. Some of them were withdrawn, most of them just sat on the preprint server, gathering electronic dust. The community moved on, but the lesson from the diphoton episode burned itself into the institutional memory of the field. 3 sigma is not enough. 3 sigma is, in fact, often nothing. So when the B-meson-lepton universality anomalies appeared a few years later, the community was already a bit more cautious. These anomalies, which I'll explain very briefly because they were the previous big hope, involved the rate at which B-mesons decayed into electrons compared to their decay into muons. The standard model predicts that these rates should be essentially identical, because the only difference between an electron and a muon is mass, and the mass dependence in these decays is small. The LHCb collaboration, throughout the late 2010s, had been seeing rates that disagreed with that prediction by about 2 to 3 sigma consistently. The pattern was suggestive. Multiple decay modes were showing the same direction of deviation. Theorists started writing papers about leptoquarks and Z-prime bosons that could explain the pattern. Then, in 2022 and 2023, LHCb did a careful reanalysis with more data and improved understanding of the systematics. The anomalies again faded away. The deviations got smaller, the patterns got less consistent. By the end of 2023, what had looked like a coherent hint of new physics had collapsed into mostly noise. Which brings me to the muon G-2 anomaly, the most famous one of the past decade, and the one whose recent fate is, I think, the most instructive. The muon's anomalous magnetic moment, abbreviated as R-mu, is one of the most precisely measured quantities in all of physics, because it is sensitive to virtually every particle in the standard model, and to anything beyond the standard model that might exist. For decades, there was a small but persistent discrepancy between the measured value of mu and the value predicted by the standard model. That discrepancy, by 2021, had reached about 4.2 sigma, based on combined results from the original Brookhaven experiment in the early 2000s and the new Fermilab muon G-2 experiment that started taking data in 2017. It was, for years, the strongest hint of new physics in particle physics. On the 3rd of June 2025, the Fermilab Muon G-2 collaboration published their final result. The number was A mu equals 0.00165920705 with a precision of 127 parts per billion. That precision exceeded the original design goal of 140 parts per billion. The result agreed with their previous publications from 2021 and 2023. It was the most precise measurement of the muon's magnetic moment ever made, and it will remain the world record for years to come. In April of 2026, just a few weeks ago, the Fermilab Muon G-2 collaboration was awarded the 2026 Breakthrough Prize in Fundamental Physics, recognizing 3 generations of the experiment going back to CERN in the 1970s, then Brookhaven in the late 90s, and finally Fermilab. So you might think this is the story of an anomaly being confirmed. It is not. It is the story of an anomaly slowly dissolving in a way that is almost more uncomfortable than if it had just collapsed outright. Because the experimental side is now closed, the measurement is done, the result is final. But the standard model prediction, the thing the measurement is being compared to, has become a battleground. There are 2 ways to calculate what the standard model predicts A mu should be. One method is data-driven, using measurements of the cross-section for electron-positron collisions to estimate a quantity called the hadronic vacuum polarization. The other method is computational, using lattice quantum chromodynamics to calculate the same thing from first principles using massive supercomputer simulations. These 2 methods give different answers. The data-driven method gives a standard model value that disagrees with the measurement by about 4 sigma. The lattice method, particularly a high-profile calculation by the BMW collaboration, gives a value that agrees with the measurement. Which one is correct? Nobody knows yet. Recent lattice work has been trending toward the BMW result. Recent theory initiative analyses have been combining methods and finding that the discrepancy is shrinking, which means that the Muon G-2 anomaly, which was for years the brightest hint of new physics in the field, is now in a position where the discrepancy may simply not exist, may just be a sign that the data-driven method had a systematic error in the hadronic vacuum polarization estimation, which, if confirmed, would be a beautiful piece of physics, a hard-won precision result and a closed door. Not a discovery of new physics, but a confirmation that the standard model can explain even this strange sensitive number. So when LHCb came out 3 weeks ago with their 4 sigma B-meson result, the community's response was very different from what it would have been 10 years ago. There was excitement, yes, but also an enormous amount of caution. The diphoton bump faded. The lepton universality anomalies faded. The Muon G-2 anomaly is fading in a different way by having its theoretical baseline shift toward the measured value. Anyone proposing new physics in 2026 knows that the institutional default response, hard-won through a decade of disappointment, is to wait for more data, to check the calculations, to verify the systematics, to not write 500 papers in 3 months, and yet. This one, just maybe, might be different. Because the LHCb result is not just a bump in a smooth background, it is a deviation in a tightly predicted angular observable. The geometry of the decay is sharp, the calculation is constrained, and the 4 sigma is not, like the diphoton, sitting in a region with a high look-elsewhere effect. It is sitting in exactly the place where new physics could appear if there is new physics to find. So the field is right now in a very specific posture, cautious, skeptical, watching, but also just a little bit hopeful. For the first time in a long time, the silence has been broken, and the next 2 years of data will tell us whether the universe was speaking or whether what we heard was, again, our own hopes amplifying noise into a signal. But what if the silence itself has been the answer all along? What if, after 30 years of patient, methodical exclusion, the universe has been telling us something we have not been ready to hear? something that would force us to rethink the assumption that has been quietly driving the entire field of fundamental physics since the 1970s. Part 12. Maybe we are not natural. I want to take you somewhere now in your imagination. I want you to float just for a moment above the plane of our galaxy, the Milky Way. From up here, you can see the whole disk, with its spiral arms unwinding across 100,000 light-years of space. The stars, hundreds of billions of them, glittering in the great wheel of the galaxy. From this vantage point, you can watch the stars move, not over years, over the kinds of timescales the galaxy itself uses, where one rotation takes about 250 million years, and our Sun has made roughly 20 laps around the galactic centre since the Earth formed. From up here, you can see what Vera Rubin saw. The outer stars, hundreds of light-years out from the bright centre, are moving at speeds that should rip them out of the galaxy. They orbit in defiance of the visible mass that the galaxy contains. Something invisible holds them in place, something that fills the space between the stars, that dwarfs the visible matter by a factor of more than 5, that has shaped this galaxy and every other galaxy in the universe. Now I want you to come closer. Drop down through the disk, pass through stars, through nebulae, through the empty space between worlds, come back to Earth. Sit in your chair, listen to the room around you. The same dark matter that holds the galaxy together is, at this moment, streaming through your body. About 0.4 giga-electron-volts per cubic centimetre is the local density. Trillions of dark matter particles are passing through you every second. They are not stopping. They are not interacting in any way you can detect. They are just there, going through you, going through the chair you're sitting in, going through the floor and the foundations of the building and the rocks below. They have been doing this for the entire span of your life. They have been doing this for the entire history of the Earth. They will continue, more or less unchanged in density, for the rest of the lifetime of our solar system. The largest machine we have built cannot produce them. The most sensitive detectors we have built cannot see them, and they are passing through you, right now, by the trillions per second. Sit with that for a second. Because what I want to say next requires you to feel the size of what is missing. In the late 1970s, when supersymmetry was first becoming the dominant framework for thinking about beyond standard model physics, the underlying philosophical commitment that was driving the predictions was something called naturalness. Naturalness is, at first blush, an aesthetic principle. It says, roughly, that the constants and parameters of a fundamental theory should not be finely tuned. That is, you should not have to adjust the parameters of your theory to many decimal places to make it match reality, unless there is some underlying reason for that fine-tuning. If you do find yourself fine-tuning, that is a sign that your theory is incomplete, and the fine-tuning is masking some deeper structure that, when discovered, would naturally explain why the parameters have the values they do. Naturalness was the engine that drove the prediction of supersymmetry. The Higgs mass, in the standard model alone, is unstable to enormous quantum corrections. Without something to cancel those corrections, the Higgs mass should be many orders of magnitude larger than what we observe. Supersymmetry naturally cancels them, because for every quantum correction from a standard model particle, there is an equal and opposite correction from its superpartner. That cancellation works automatically, but only if the superpartners are at masses near the TeV scale, which is exactly the scale the LHC was designed to probe. Naturalness, in other words, predicted that supersymmetry should appear at the LHC. It was not just a guess. It was a deeply motivated, theoretically beautiful prediction. That prediction has now, after 14 years of data, been pretty thoroughly broken. The LHC has not found supersymmetry. The natural region of SUSY parameter space has been excluded, which means one of two things. Either supersymmetry exists at much higher masses than we expected, in which case it no longer solves the hierarchy problem cleanly, and the original motivation dissolves, or supersymmetry does not exist at all, in which case the Higgs mass really is finely tuned and we have no explanation for why. Either way, the assumption of naturalness, which has been driving particle physics theory for 50 years, is in serious trouble. And here is where the story gets philosophical and a bit uncomfortable. Because if naturalness is wrong, if the universe really does just have finely tuned constants without any deeper explanation for them, then we are forced to confront an old idea that physicists have for a long time found distasteful, the anthropic principle. The argument made famous by Steven Weinberg in the 1980s when he was trying to explain the small but non-zero value of the cosmological constant goes something like this. There may be many universes, or many regions of one big universe, or many possible solutions to whatever the underlying theory is, and in each of those universes or regions, the fundamental constants take different values. In most of them, the constants are such that no observers like us can exist. The constants are too large or too small or wrong in some way that prevents galaxies or stars or chemistry from forming. We find ourselves in a universe with the specific constants we observe because in any other universe we would not be here to observe anything. The constants are not fundamental. They are selected by the fact of our existence as observers. This is, I think, one of the most uncomfortable ideas in modern physics, and it is uncomfortable for a very specific reason. It is, by its nature, untestable in the traditional way. We cannot, even in principle, observe other universes to check whether their constants are different. We cannot verify the multiverse. The anthropic principle is a kind of meta-explanation that, depending on your philosophy of science, either represents a profound insight about the nature of physical law or represents a complete abandonment of the explanatory project that has driven physics for 400 years. Steven Weinberg, who was one of the most respected theorists of the 20th century, took the anthropic principle seriously. He argued in print that the cosmological constant, which is a fantastically small number that has no good explanation in the standard model, might just be anthropically selected. Other physicists, and it is a long list including some of the most thoughtful people in the field, find the anthropic principle deeply unsatisfying. They argue that adopting it amounts to giving up. But here is the thing that has changed in the past decade. The empirical pressure on naturalness has gone up, and gone up dramatically. The LHC's failure to find supersymmetry is the strongest empirical pressure on naturalness in 50 years. And as that pressure has grown, more and more serious physicists are quietly saying, in conferences and in private conversations and occasionally in print, that maybe the anthropic principle was right after all. Maybe the universe is finely tuned, and the explanation for the tuning is selection, and there is no deeper underlying mechanism. Maybe naturalness was a metaphysical preference, a beautiful idea that we wanted to be true, and the universe simply does not work the way we hoped. I want to pause here and do something the outline asked me to do, which is to address, briefly, the conspiracy theories that have grown up around CERN, because I think the pattern is illuminating. There are theories that CERN is opening a portal to another dimension or to hell. There are claims that the CERN logo is hidden satanic symbolism. There are people who point at the statue of Shiva at the entrance to the main building as evidence of some hidden agenda. The Shiva statue, by the way, was a gift from the Indian government in 2004, when India became an associate member of CERN, and the cosmic dance of Shiva is a traditional Hindu metaphor for the dynamic equilibrium of fundamental forces, which is exactly what particle physics studies. The logo is a stylized depiction of overlapping accelerator rings. There are no portals to anywhere. The energies involved at LHC collisions, while enormous in particle physics terms, are trivially small in macroscopic terms. The total stored beam energy in both beams is about 360 megajoules, which is comparable to the kinetic energy of a high-speed train. A train. Not, a planet buster. But I do not think the conspiracy theories are interesting because they are right. I think they are interesting because of what they reveal about how people respond to the specific kind of unease that is in the air around fundamental physics right now. The conspiracy theorists are picking up on something real, even if they are wrong about its meaning. They are picking up on the fact that something promised did not arrive, that the cathedral was built and the god did not show up. They feel the silence, the same silence that the field is feeling, and they explain it with stories of hidden portals and secret discoveries. The legitimate philosophical worry, which is that naturalness might be wrong and the universe might be anthropically selected, is, in its own way, just as unsettling as any portal story. It is just unsettling in a way that can be expressed only in equations and conferences, not in viral videos. The fringe is reading the same silence everyone else is. They are just attaching the wrong meaning to it. So this is where the field finds itself in 2026. Naturalness, the philosophical engine that drove 50 years of theoretical work, is under the strongest empirical pressure it has ever faced. The dark matter, which was supposed to be a free byproduct of solving naturalness, remains stubbornly invisible. The LHCb anomaly might be the first crack in the silence, or it might be another diphoton ghost. The neutrino flaw in the underground detectors marks a hard physical wall to one of our two main approaches. And yet, despite all of this, despite all of the silence and all of the disappointment, the field is not giving up. It is, in fact, doing something remarkable. It is asking for a bigger machine. Part 13. The $1 billion bet. In November of 2025, the CERN Council met in dedicated session over 2 days to formally review the Future Circular Collider feasibility study. The feasibility study had been running for years, conducted by an enormous international working group, examining every aspect of what it would take to build the next generation collider after the LHC geological surveys, civil engineering plans, magnet R&D, detector concepts, tunnel routing, environmental impact assessments, cost projections, the works. After 2 days of presentations and discussions, the Council formally confirmed that the project is technically viable and free of major obstacles. The path is clear. The next big decision, the formal go or no-go on the European strategy update, will be made by the Council in May of 2026. The final full construction commitment is expected around 2028. A month later, in December of 2025, CERN made an announcement that, in the 72-year history of the institution, was unprecedented. They announced that a group of private donors had pledged 860 million euros, which translates to about $1 billion toward the construction of the Future Circular Collider. The donors are the Breakthrough Prize Foundation, which is funded by Yuri Milner, the Russian-Israeli internet billionaire who has been a major patron of fundamental science for over a decade. The Eric and Wendy Schmidt Fund for Strategic Innovation, founded by the former CEO of Google, John L. Kahn, who is the head of the Agnelli family business empire in Italy, and Xavier Niel, the French telecom and media entrepreneur. Together, these four sources pledged $1 billion, which is roughly 5% of the projected total cost of the project. I want to slow down on this because I think the cultural significance of this announcement has not been fully appreciated yet. In 72 years, CERN has never before accepted private donations toward a flagship machine. Every previous instrument, including the LHC itself, was funded entirely by the member state governments. 23 countries chipping in on a defined formula year after year to build the cathedrals beneath the Swiss countryside. The December 2025 announcement broke that precedent. It is the first time in CERN's history that private money is helping to build the future of particle physics. It is, by some distance, the largest private contribution to fundamental physics infrastructure ever made, and it shifts the political calculus around the FCC in a fundamental way. The Future Circular Collider, if approved, would be a tunnel 90.7 kilometers in circumference, sitting between 180 meters and 400 meters underground, depending on the local geography. That circumference, 91 kilometers, is more than 3 times the size of the existing LHC tunnel. The tunnel would be built in the Geneva Basin, with 8 surface sites, 7 of them in France and 1 in Switzerland. The plan is for 2 phases of operation. The first phase, called FCC-EE, would be an electron-positron collider designed to function as a so-called Higgs factory. It would produce huge numbers of Higgs bosons in clean, well-understood collisions, allowing physicists to measure the Higgs's properties with extraordinary precision. Any deviations from the standard model in those properties would be an indirect probe of new physics at scales the LHC cannot reach. The second phase, called FCC-HH, would reuse the same tunnel but with a much more powerful magnet system to operate as a proton-proton collider at a centre of mass energy of about 100 TeV. That is roughly 7 times the energy of the LHC. At those energies, you could directly produce particles up to mass scales of about 12 TeV, which is well above where the LHC has been able to look. If new physics is sitting at scales just above the LHC's reach, the FCC-HEH would find it directly. If it is not, the FCC-HEH would push the exclusion limits another order of magnitude further into the desert. The total cost of the project is estimated at around 16 billion euros, with construction starting in the late 2020s and operations beginning in the mid-2040s. The first phase, FCC-EE, would run for about 15 years. The second phase, FCC-HH, would follow in the same tunnel after another major upgrade. Most of the people who are currently graduate students, who would be the ones building and running the FCC, would be in their 50s and 60s before the second phase produced its first definitive results. This is a generation-long commitment. Possibly 2 generations, which is exactly the kind of commitment that government funding cycles, with their 3 to 5 year horizons and their political weather, cannot really make, which is why the December 2025 private pledge matters so much. Because private philanthropy, particularly from people like Yuri Milner, who have explicitly framed their giving as a long-term bet on humanity's scientific mission, can commit on time horizons that no government can match. There is a competing project, the Circular Electron-Positron Collider, that was being seriously considered in China. The CEPC was, at one point, a real challenger to the FCC, proposing a similar 100-kilometre tunnel for similar Higgs factory physics. As of 2025, the CEPC was effectively shelved when it was not included in China's 2026 to 2035-year plan. Wang Yifang of China's Institute of High Energy Physics has said they will resubmit the CEPC for consideration in 2030 unless the FCC is officially approved before then. So the next generation collider race, which had been a real 2-horse race for years, is now mostly the FCC, with the CEPC waiting in the wings as a backup. So here is the picture in 2026. The LHC has run for 14 years and has not delivered the predicted breakthrough. The underground detectors are approaching the neutrino floor. The LHCb anomaly is sitting at 4 sigma and waiting for Run 3 data to clarify it. And the field, in the face of all of this, is asking governments and private donors for another 16 billion euros and another 20 years to build a bigger cathedral. The remarkable thing is that the field is getting what it asks for. The November 2025 Council review was favourable. The May 2026 European Strategy decision is expected to recommend the FCC. The 2028 construction decision is expected to approve it, and $1 billion of private money is already pledged. The silence has not produced surrender. It has produced commitment to a generation-long answer. But why? Why are we still building after 30 years of being told no? What does it mean to commit to another 20 years of looking, when the looking we have done so far has produced exactly one discovery, exactly one, and an enormous, accumulating, careful absence of the rest? To answer that, we have to confront the most uncomfortable interpretation of the silence, the interpretation that some of the most respected theorists in the field are, in their honest moments, beginning to consider seriously. Part 14. The Honest Reckoning. I want to spend some time on something that is rarely said cleanly, because it requires sitting with disappointment in a way that academic life does not always reward. What if the silence is the answer? What if there is no new physics at the energy scales we can reach? What if the standard model, to the precision that any conceivable experiment in the next century can probe, is just complete? Not as in fundamental, because we know it is incomplete. We know it does not include gravity. We know it does not explain dark matter or dark energy or the matter-antimatter asymmetry of the universe, but complete in the limited sense that, within the energy regime where we can do experiments, the standard model fits the data, and there is no new physics waiting at higher energies that we will be able to access in any reasonable time frame. This scenario has a name in the field. It is called the desert. The idea is that there is a vast empty energy desert between the TV scale, where the standard model is tested, and the Planck scale, where gravity becomes quantum, 16 orders of magnitude higher in energy. In between those two scales, in the desert, there is nothing. No new particles, no new forces, just the standard model, alone, ruling over an enormous range of energies that no terrestrial experiment will ever directly probe. If the desert is what we have, then the future of fundamental physics is going to look very different from its past. The past century of physics has been a parade of new particles being discovered every decade or two. The electron, then the proton, then the neutron, then the muon, then the pion, then the strange quark, then charm and bottom and top, then the tau, then the W and Z bosons, then the gluon, and finally, in 2012, the Higgs. A century of discoveries. If the desert is real, the Higgs may be the last fundamental particle we ever discover. The next bigger collider, the FCC, may run for 15 or 20 years and find nothing new, just push the exclusion limits another order of magnitude into the desert. The collider after that, if it ever exists, may do the same. We may have, without realizing it at the time, lived through the last great age of particle discoveries, and the future may be one in which the standard model, like the periodic table, is just complete to the precision that matters for any practical purpose. I want to stress that we do not yet know if this is the case. It is one possibility among several. New physics could exist just above the LHC's reach, and the FCC could find it. New physics could exist in what physicists call long-lived particles, things that decay outside the detector volume and require special-purpose searches like FACER and MOIDL and the proposed Methuselah detector. New physics could exist in feebly interacting hidden sectors or in places we have not been smart enough to look yet. The silence does not prove the desert, but the silence is increasingly consistent with the desert. And the longer the silence goes on, the more the desert hypothesis gets weighted in the prior probabilities of careful theorists. What does it actually mean, emotionally, to be a physicist in a field where the dominant interpretation of 3 decades of data is starting to look like the desert? I want to try to convey this honestly, without naming specific people, because the structural feeling I am trying to describe is much bigger than any individual experience. Imagine you are a theorist in the late 1990s. You're a graduate student. You're watching the field around you converge with confidence and excitement on supersymmetry. You write a thesis on a specific corner of supersymmetric phenomenology. You imagine, in your career, that the LHC will turn on, that the superpartners will be discovered, that you will work for 30 or 40 years on understanding the implications. You become an assistant professor in 2005. You become tenured in 2012. You publish papers throughout. The LHC turns on. The data comes in. The superpartners do not appear. Year after year, you watch the natural region of your favorite parameter space get cut down. The phenomenology you wrote your thesis about becomes irrelevant. The framework you built your career on, while not strictly dead, becomes, in the eyes of the field, less and less plausible. You did not do anything wrong. You did not make a calculational error. The math, on paper, was beautiful. You took your best shot at the hardest problem and did the science honestly. But the universe, for whatever reason, did not arrange itself the way the framework predicted it would. And now, in 2026, you're in your 50s or 60s, and the next generation collider that might confirm or refute the assumptions you built your career on will not produce its first definitive results until you are retired. Maybe not until after you're gone. This is not an unusual story. It is in fact the story of much of the senior theoretical physics community in 2026. These are not failed scientists. These are scientists who took their best shot at the hardest problem and did the science honestly. And the science honestly, it turns out, is sometimes a process of finding out that your framework was wrong, or that the universe just was not, in the way you had hoped, structured around the principle you were assuming. There is, I think, real dignity in the way the field has handled this. Theorists have not gone into denial. They have mostly been honest about what the data says. They have proposed new candidates for dark matter. They have proposed new frameworks. They have continued to work, even as their original frameworks have been winnowed down. And they are now, in 2026, asking governments and private donors to fund the next stage, not because they are confident that the FCC will find something, but because they are honest enough to say that finding out for sure, finding out whether the desert is real, or whether the new physics is just one step further out, is itself worth the price. Which is a profoundly different answer than the one the field would have given you in the year 2000. In 2000, the answer would have been, build the LHC, find the supersymmetric partners, identify the dark matter, solve the hierarchy problem, complete the framework, retire. In 2026, the answer is, build the FCC, push the limits another order of magnitude, see what happens, accept that the answer might be that the answer is not findable in the way we've been looking. This is, in its own way, a more mature posture, a more honest one. It is also a much harder one to sell to funding agencies and to the public, which is why the December 2025 private pledge matters so much. Because at this point, the field is not really pitching a guaranteed discovery. It is pitching the value of knowing for certain whether or not the discovery is even possible. And yet, despite all of this, despite the desert and the silence and the dignified acceptance, the LHCb whisper sits in the data. 3 weeks old, 4 sigma, run 3 data already on disk and being processed. The first multi-sigma anomaly to survive scrutiny in 5 years. Nobody knows yet what it means, but somebody, somewhere, in a control room beneath the Franco-Swiss border, in a quiet office at Imperial College London, in a theory department in Boston, is right now, tonight, looking at a plot, and feeling something they have not felt in a decade. Hope. Cautious hope. The kind of hope that has been disappointed too many times to be wholehearted. But hope nonetheless. Part 15. The silence is the discovery. Let me take you back to the LHC tunnel one last time, because I want to end this video where it began, in the place where the question is being asked. It is somewhere around 3 a.m. Geneva time. The tunnel is dark except for the maintenance lights and the soft glow of the magnet status indicators. The proton beams are circulating in opposite directions in their evacuated pipes. The magnets are cold. The detectors are recording. The collision points are doing what they have been doing for 14 years, 40 million times per second, in their relentless mechanical patience. In a control room above ground, a graduate student is watching an event display on her monitor. The display updates in real time, showing the tracks of charged particles spiraling through the calorimeters of the Atlas detector. Each new collision flashes across the screen. Most of them are mundane, standard model events, a quark gluon vertex, a pair of jets, a muon track curving through the magnetic field. The student has seen thousands of these tonight. She will see thousands more. Once in a while, the trigger system flags a high-energy event, and everyone in the room leans in for a moment to look at it, and then leans back when the event resolves into a familiar standard model signature. The rhythm of the room is the hum of the cooling systems, the soft chatter of the shift crew, the periodic quiet of the trigger pings, and then the quiet again. She does not know whether the work she's doing tonight will be remembered. She does not know whether the LHCb anomaly will firm up into a discovery, or fade into the graveyard of vanished hints. She does not know whether the FCC will be approved in 2028, whether her career will involve building it or doing something else entirely. She does not know, when she walks home tonight under the stars, whether the dark matter passing through her body is a particle, or a modification of gravity, or something nobody has yet conceived of. She's doing the most important work of her professional life without knowing whether the answer she is searching for can be found at all. There is a phrase I've been saying through this entire video: the cathedral was built. The god did not show up. I have used it as a kind of dark joke, the line that physicists tell each other in hallways. But I want to put it down now, gently, for the last time, because by this point in the video I hope it sounds different than it did at the beginning. I hope it sounds less like a punchline and more like an honest description of where we are. The cathedral was built. It is to this day the most ambitious and beautiful piece of scientific infrastructure ever constructed. The god did not show up. Not yet. Maybe not ever, in the form we expected. But the silence that the cathedral has produced, the silence that has filled the past decade, is not, I think, an absence. It is information. It is, in its own way, the most precise empirical statement physics has ever made about what reality is not. The Standard Model is more thoroughly verified than anyone in 1990 expected it would be by 2026. The natural region of supersymmetric parameter space is empty. The WIMP is not at the masses where the simplest theory said it should be. The cosmological constant is finely tuned, and we have no good explanation for the fine-tuning. The dark matter, which makes up over a quarter of the universe by mass energy, is hiding from every approach we have devised. And in the last 6 months, 2 new things have happened that complicate the silence in interesting ways. The LZ detector, a mile beneath South Dakota, has crossed into the neutrino floor, telling us that one of our 2 main approaches to dark matter is approaching a fundamental physics wall. And the LHCb collaboration, in a tunnel beneath Geneva, has produced a 4 sigma anomaly in B-meson decays that, if it survives the next 2 years of data, will be the first crack in the Standard Model in 50 years. 95% of the universe is missing. That is not a temporary state. That has been the state since we figured out how to measure it. It will continue to be the state for the foreseeable future. The missing is not a footnote in a textbook waiting to be revised. It is a permanent address. The universe we live in is, by mass energy, mostly a mystery. And the most powerful instrument we have ever built, after 30 years of looking, has told us, in great detail, where the mystery is not. It has not yet told us where it is. There is something to be said for the dignity of that. There is something to be said for a species that builds a 27-kilometre ring of magnets, 100 metres underground, runs it for 14 years, finds the thing it predicted it would find, and then sits, patiently, with the news that the rest of what it expected to find did not arrive. There is something to be said for being honest about the silence, and asking, with care, what the silence might mean. There is something to be said for committing another $1 billion and another 20 years to keep listening, with the full knowledge that the listening might continue to produce the same kind of silence, and that the silence is itself a kind of answer, and that learning the shape of an answer we cannot yet name is, on its own terms, a thing worth doing. The silence is the discovery. I said it earlier as a hallway joke. I want to say it now as the actual thesis. Not because there is nothing to find, but because the shape of what we have not found, after 30 years of carefully looking, is itself the most informative thing we have learned. The shape of the silence tells us that the universe is not what we expected. That naturalness is, at minimum, suspect. That dark matter is not made of the simplest thing we could imagine. That the deepest structure of reality may not be accessible to us through the methods we have been using. And that the next layer of physics, if there is one, may require either a much bigger machine or a completely different way of asking the question, or both. The graduate student in the control room does not know whether she is at the beginning or the end of an era. She's watching event displays. She's doing her job. The proton beams are circulating in the dark beneath her feet. The magnets are cold. The LHCb detectors are recording. Somewhere in the data being written to disk tonight is, possibly, the answer to whether the 4 sigma whisper from 3 weeks ago grows or fades. We will know within a few years. The silence will perhaps break, or the silence will perhaps continue, and we will have to learn what to make of it. In the meantime, the universe continues to do what it has always done. The dark matter continues to pass through your body by the trillions per second on its way to wherever it is going. The sun continues to pour out neutrinos that were, until 2025, beneath the threshold of our most sensitive detectors and are now just barely above it. The galaxies continue to rotate at speeds that should fling their outer stars into the dark, held in place by something that does not glow. And we, the species that built the cathedral, continue to listen. To listen and to ask with growing patience what the silence means. To ask whether the absence we have been measuring is the absence of something we have not yet found, or whether it is the absence of something that was never going to be there in the first place. Either way, the asking is the thing, even when the answer is silence, especially when the answer is silence. Because the silence, after all, is what the universe has chosen to say back to us, and learning to listen to it carefully, without forcing it into the shape we wanted, is maybe the hardest and most important work fundamental physics has left to do. The magnets, in the dark, continue to hold their cold. The protons continue to circle. The whisper, 3 weeks old, continues to wait for the data that will tell us whether it was the cathedral speaking or the cathedral settling. And we, all of us, continue to ask the question that has been the spine of this video from its first sentence to its last. If the most powerful instrument we have ever built has finally, after a decade of silence, started whispering back, what exactly is hiding inside the data? And are we ready this time to hear what it says,